recording. Okay, so here is an exam. Like I said, it's in Hebrew, but I can just skip all the instructions. You see here it says though 120 minutes, and it says you can use the choveret as there. That there's going to be some kind of list of all the commands on in a booklet. And it's, like I said, 99.9% English. Maybe there's a title or something in Hebrew. And also there's a daf, a page with system calls on it. Okay, the rest is, you also could have a machshavon pashut. You could have a simple calculator, if somebody asked. This is the way it was last year. And it says 3 questions. Actually, this is totally different structure from the Mivchan of this year. I mean, it is a sample exam, but I'm not going to write a whole new exam. The new structure is going to be multiple choice. I wrote a couple questions for it, and I can tell you, I wrote for the Moed Bet only, and I'll tell you what I'm permitted to tell you is the following: that I definitely have a question of, here's a line of code. What is the kidud? What is the kidud? What is the encoding of it? How will it look in ones and zeros? But of course, in hexadecimal. In other words, how will this code look in hexadecimal? Which
like you give us a command and we have to.
I'll give you a whole program, and I'll say the line here that's with the add or with the branch or with the load word. What would the kidud be of this load word here? Or what would the kidud be of this SLT?
Well, can you say
kidud? I'm saying in Hebrew, encoding.
Okay.
Encoding. Sorry, kidud is Hebrew for encoding because it comes from the word code. With kaded would be to encode something. So the encoding. What would the encoding of it be? Well, how does it look in hexadecimal? But let's see what this exam has on. Okay, let's start with the first question. Given the following program. Here you go. He gave you a program. This is a program. You say, what the heck is that? It doesn't look like a program. It is a program. It's a program encoded in hexadecimal. This is the other way around. Right? No. The address of the first line is 400,000 hex. Okay, that's a given. He's giving a bunch of natunes. He's giving a bunch of givens here. That's the way he likes to do it. It gives you all the givens. First of all, it's on line 400. Well, that's kind of obvious. In general, he just tells you that so that you shouldn't think, well, I don't know where this is in code. I don't know what line this is. I don't know where it is in memory. Every program that you ever wrote started at 400,000. He's just telling you it's starting at 400,000. Now it says like this. Before we actually ran the program, all the resistors, all the registers are equal to the number of the registers. In other words, register 4 has value 4 in it. Register 5 has value 5 in it. Of course, that's not normally the case. Normally, all the registers would be 0. So he's saying, let's assume that all the registers have the number of the register is also their value. And the address and the content of every byte in the memory is equal to the lower the lower byte of its address. In other words, the 4 LSB, the 4 least significant bits. In other words, if you have address 0 in memory, its value is going to be 0. Address 1 will be 1. But address like some very large number, it will be its value of that address will just be whatever the value of the 8 rightmost bits of that address are. So in other words, the value of address 100,000 hex will be 0 because 100,000 hex ends in 0. So the last 4 bits are also 200,000 hex will be 0. But 200,004, its value will be 4. In other words, every byte in memory, which memory starts at 10 million, all of them from the, and that's what he means when he says memory. He means, it doesn't obviously mean the memory of your code. That wouldn't make sense. But the memory from 100,000, from 10,000 and above, the values in them are equal to the lower bits. He says, for example, given the memory location 1, 2, 3, 4, 5, 6, 7, 8, the value in that location will be the right 4 bits, the right 8 bits, which is these 2 hexadecimal numbers, because remember each hexadecimal number is 4 bits, so it'll be 78. Now he says like this. Here's the first question. What is the value of register number 10 after these 2 lines have been executed? So first of all, what's the value of register 10 according to his givens before we executed these lines? That's your first step. And I want an answer. He gave it to you. I said it to you. I read it to you.
It's 10. 1, 0, 1, 4.
Exactly. Every register has the value of its number, 10. Okay. So now what is it going to be after these 2 lines are executed? So in order to do this, we need to do some work. We need to figure out what this first line is. So the first step and most important step is to figure out the opcode. What's the opcode here? The opcode is the first 6 bits. So what's the opcode here? Well, like I said, every digit here is 4 bits. So what's the first 6 bits of this? 8 is what? 8 in 4 bits is 1, 0, 0, 0. So we know it starts 1, 0, 0. So we know already it's not an R type because it doesn't start with 0. It's 1, 0, 0, 0. And then 2 more zeros are part of this 3. This 3 is actually, how do you write 3? You write 3, 0, 0, 1, 1. So we know that the first 6 bits, therefore, must be 1 followed by 3 zeros and then another 2 zeros. So that's a 1 followed by 5 zeros. What is that value? One
32.
Followed by, where is it? One followed by 5 zeros.
32.
So 32. Yes, 32. So it's 32. So now we've already figured out the opcode is 32. Everyone see how we got 32? 8 is 1 followed by 3 zeros, and 3 is 2 zeros followed by 2 ones. So we ignore the 2 ones because they're not part of the opcode, and we take the first 6 bits and we get 32. So now, do you see my new page? Do you see the Machon Lev page?
Yeah.
Okay, so let's go to here. Let's go to here. No, the wrong place. I need to find out what 32 is. So you will have on the exam, I want to use the exact thing that you'll have on the exam. Oh, but I don't know if it's here. No, it's not here. It's actually, it's in the course itself here. And you have, here, Choveret Ezer Levchan. I think this is it. Oh, well, now you're not going to see it because it's in Word. Just a second. Let me change my share. Stop share, and let me share. Here, I'll share the screen. Okay. So it's Choveret Ezer Levchan, a helping booklet for the exam. And the syscall pages. Here's the diagrams. Oh, this is more for the other course. You see the diagram is in English. It just says Ma'bed Chad Machzori, single cycle. And here it says Rav Machzori. Rav means many, many cycles. You can tell by just looking at the CPU, it's got a lot of lines. That's the many cycle. And here is the thing that interests us, which is common MIPS instructions. And we need to find one. Wait, let's see. Common MIPS. Ooh, we need to find one that's 32. I hope it's here. 32 in hex is 20, right? And these numbers are in hex. So we're going to look for 20 over here. Maybe we passed it. Oh, no, that's 020. That's not right. Oh, I guess there it is. 20. What is 20? It's load byte. All right, that helps us out a lot. So we know that it goes, that the way you write the command is like this. LB, LRT, offset RS. Now remember that the order is switched in the actual encoding. We put the RS always first. So it's going to be RS, RT offset, actually. But that tells us already the structure of what we're looking at. So now if we go to the exam again, where was it? Here. Let me stop the share. Well, yeah, I'll leave the share open, fine. And we see that, what is this command? Well, oh, can I do, here, let's see. I want, where's all my annotate? Ah, here we go. Text. So we figured out that it's 32. So the first bits are 1, 0, 0. Let's do another text box. Right. Text. No. Oh, you can't do two text boxes? I don't know. Okay. So we said the kidud is ones, we followed by 4 zeros, then 2 more zeros. That's the opcode 32. Then we have 2 more ones for the 3, followed by the 0, I'm looking at this 0 over here. That's 4 zeros. 1, 2, 3, 4. Followed by a 4. 4 we're going to write as 0, 1, 0, 0. Followed by 3 more zeros, which means 3 times 4 is 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then a 4 at the end, which will be 0, 1, 0, 0. That is, my friends, the binary of this command, which is, of course, much easier to look at, the binary, because now we can divide it up any way we want. This is divided by 4s. We want to divide it by different numbers. We want the first 6 is the opcode. The next 5 is the RS. What's the RS here? RS is that value. What's that value? It's 16 and 8, 24. Agreed? It's 24. So we're saying take register 24. Well, that's the RS. And what's the RT? The RT is again, this is 24 is 5 bits. The RT is also 5 bits, which means all this, right? This is 5, and this is 3, this is 5. So all this. So what's this value? 1, 2, 4. So the RT will be 4. Okay, that's good enough. Let's write that down. You know, so remember it. I'm writing it down. You can write it down. RS is 24. RT is, what did I say? 4. Right? 1, 2, 4. And that's 16 and 4 and 8 is 24. That's the RS. And now, what's the value over here? Well, this 16 bits we look at as one group, and the value is 1, 2, 4. 4. Okay. So let's go back to our Word document. Oh, I gotta go like this. And here. And let's look at the LB command again. We take the RS, which is 24, and we go to that memory location, 24, and so what do? We go to what's in register 24, and we add to it 4, and we load that byte into register RT. We're loading it into RT. So RT's value will be what? Can you tell me what RT's value will be?
28.
How'd you get that?
Well, you said that the registers all start off with what they are. So in register 24 would be the value 24, right? And then if you go 8 bytes later.
No. In register, oh, I see, sorry. You're right. Take it back. Yes, RS is register number 24, and the value in every register is 24. So we're going to location in memory 24, which also, well, what did it say? Also, no, the memory, you got to add one more step. That the memory has in it what? The location of the byte, of the leastmost byte of its spot. Well, it just so happens that 24 is all zeros, and the leastmost spot value is also 24. So it comes out that in this case, that register 24 points to memory location 24, and memory location 24 has the value 24. That's what you want. That's the full state. And then, but that's not the one we get. Which one do we get?
Memory location 28.
We get 28. We get location 28. because we added an offset to it of 4. So we got location 28. What's in location 28? In memory, location 28 is the value 28. True. So what's going to be now in RT? It used to be in RT was the value, in register 4. Wait, RT is 4, but now we'll be in it 28. Okay, so now we can say RT is value is 28. Or actually better than RT, that's really not useful to say RT is 28. What's really useful is to say register 4, his value is 28. You understand? Because register 4 is the RT. If I go back to my other picture. Register 4 is the RT. And we just put into it value memory location 28 plus 4, 24 plus 4 is 28. We put in it value 28 into register 4. So even though you said every register holds its value, like it says here, example, register 4 has the value 4. Well, actually not anymore. Register 4 now has the value 28. Anybody have a question on how we got that?
You said at the beginning that every byte in memory holds the value of the last 2 bytes of its memory's location, right?
Last single byte.
Oh, the last single byte.
That it has to be that way because it can't. 1 byte can't hold the value of 2 bytes.
Makes sense.
Right. Okay. So now, but that's not the question. The question was not what's in the value register 4. The question is what's in the value register 10. Well, we haven't even touched register 10. So we're gonna have to do the key dude. We're gonna have to do we're gonna have to undo the key dude. We're gonna have to extrapolate what this is, what this code is, and figure out what this does. Maybe he will affect the number 10. So far, we haven't affected number 10 at all. What is this? This is number 10. Okay. What is this kind of? This is 0, 1. Well, 0, 1, if we take the first 6 bytes, what are we going to get? I got to do a new text box. Text. So what is 0, 1? Well, it's 4 zeros followed by a 1, which is 2 zeros and a 0 and a 1. So we know that the opcode is 0. What opcode? What does that mean if it's opcode 0?
It's an R type.
Very good. It's an R type. That's going to help us. We still know what R type. In order to find out what R type, we're going to have to look at the end here. So let's do the whole thing in binary. E. What's E? E is, well, A is 10, B is 11,
14.
C is 12, it's 14.
14.
Thank you. I'm slower. So 14, what's the key do to 14? It's 8 and 4 and 2. That's 14. That's our E. And now 4. That's 0, 1. Oh, let's put a space. 0, 1, 0, 0. That's our 4. And 5, 0, let's put a space. 0, 1, 0, 1. 0, that's 1, 2, 3, 4. 2, 0, 0, 1, 0. And 4, 0, 1, 0, 0. That is the binary. And that allows us now to, why we put it in binary, so that we can divide it up properly. That's the first, that's the opcode. The next 5 is, well, it's an R type. So the next 5 is the RS. So how many is that? That's here, right? That's the RS. 0, 1, 1, right? That's 3, 4, 5. And the next 5 is the RT. And that's 5. And the next 5 is the RD. The next 5 is ignored, basically, is the shift amount, which is all zeros. We're going to ignore that. And here is the crucial part, the function code, these 6 bits at the end. What is that value? Well, that's 16, or no, that's 32. Well, we need to know what it is in hex. Well, sorry, it's 32 and 4, right? 1, 0, 1, 0, sorry, 1, 2, 4. So 32 with 4, 8, 16, 32 and 4 is 36. What's 36 in hex? 24. So we're going to look for in our covariate, in our booklet, we're going to look for 24 as the function and 0 as the. So let's do that. Still in this. So we need some R types. Here we have this R's. We need, what did I say? 24. Ooh, oh, I think I saw it there. Yeah, there it is. And
No.
yeah, everyone understands why I'm saying it's and? Anyone has a
Last
question?
time when we looked for 20 for 32, we looked for it in hex.
We're looking for it in hex again too. It wasn't 24. The value we're looking for is 36.
Ah,
So I
right.
told you that in hex that's 24.
Right.
Just, yeah. 16 and 16 is 32.
Yeah, fine.
What?
Fine.
Okay. So we're looking for 24 and we found it. So it's and. And what it does is it takes the RS and the RT and it ands them together and puts the result in the RD. Fine. So let's go back to our.
Wait, can you stay here for a second?
Yeah. I mean, this should be very helpful because this is exactly what you're going to have to do in the exam. You're going to have to use this booklet.
On this page somewhere, does it say how R, I, and J types are broken up?
That's a good question. I hope it doesn't say. I mean, not because I'm mean, but because I want you to know. But it might. I don't know. You can look in your here. Yeah, here it does. R, I, and J. See?
And this is what we're getting on the test.
Yes. Yes. I mean, unless there's some terrible misunderstanding. But yes, you're supposed to be getting this. I don't think you're getting all this? That would be really nice. This, I'm not sure if you're getting. Maybe you are. This is the detailed. This is the detailed code. Branch, unequal, all the different parts, RS, which bits it is, each individual command, what it does. This is the very detailed one also. I guess you're getting this. I mean, I opened up the page that said, covariate for both courses. This is the booklet for both courses. So yes, you're getting all that. You're going to have, sometimes it's a curse to get all that information because you spend all your time looking in the booklet for something instead of thinking. But I think actually in this case, it's not too much information. Okay, so we have to figure out what this command is. We figured it out, it's and. So we're done with the opcode and with this. And we're just looking at these 3 parts. This is the RS, RT, and RD. RD is going to get the and result of these 2 registers. So we want register number what? Well, that's F, right? So it's register number 15. Have we changed 15? No. So it's going to be register 15 is going to have the value 15 in it. Now, in order to do this, you're going to have to actually write another block. And you're going to say, here's register 15. It's going to have value 15 in it, which means it's going to look like this. A whole lot of zeros, and then 1, 1. I mean, I didn't write the right number of zeros, but something like that. That's register 15. And we're going to AND that with register 0, 1, 4. Ah, 4. That's our friend from before.
You
And
have an extra
4's
one in that
value
line.
is what? Who remembers?
28.
What's 4's value?
28. But you have an extra one in that line.
Oh, yeah? Here. I have an extra one in that line? Well, I just read a whole bunch of zeros, and then it should be 4 ones. It should be like that. 1, 2, 3, 4. Okay. And we're
Wait,
gonna, is that good?
Yeah.
And now let's do,
can I ask a question about what we did before we go on?
yeah.
Sorry, we said that like in register 4 is number 28, but now I'm getting confused because didn't we say that in each place in memory is like what's stored there is the like last byte of what it is?
Yes, we said that.
So
Can
then,
anybody, yeah, and how come by 4 it's not true? Anyone remember? Anyone tell us? Why is not true by 4? Because of this little line here. We changed 4. That's what we did in the first line of our program. It's true that they have initial values of whatever registered in, but it doesn't mean it's going to stay like that forever. We already did the calculation of this line of code and figured out that what it does is it puts the value 28 into register 4. So now we're using register 4. It's still got the value 28 in it.
I'm saying it didn't go to memory 28 and see what's in that spot of memory.
No, it was a load byte. It not only saw what was there, but it loaded it into a register. Which register? Register 4.
But loaded the address.
Value. What?
The value in that address, in address 28 was 0, right?
No, the value in the address 28 was 28. Oh, that was another line that's written here in Hebrew that I translated, but I didn't write down, which is that it says that not only does every register have its value, but every memory location has the value of its least significant byte. 28 happens to have, so therefore memory location 28 will have the value of the least significant byte of memory location of the number 28. Well, it just so happens that 28 fits into a byte. So,
Oh, okay. I was thinking about bits, not bytes. And
yeah.
the least significant bit would be 0, but not byte. Okay, thank you.
Right, bytes, right. Okay, so yeah, very important to remember what bits and bytes are. So now we got to write 28. Well, 28 is the same thing as 16. Let's say 16 and 8 is 24 and 4 is 28.
0, 4.
And 0 for 2 and 0 for 2. So now we just got to line this up and do an AND. Well, all these zeros will be zeros. And this 1 and 0 will be 0. 1 and 0 will be 0. But the next two will be 1. 1 and 1 is 1 in AND. Do 1 and 1, you get 1. So we'll get the value 8 and 4. And no 2 and no 1. 8 and 4 is 12. So the answer to the question is, wait a second. What's RD?
10.
RD is 10. 1, 8, and 2 is 10. So RD is 10. So we're actually going to put our 12 into 10. So the answer is the value in register 10 is 12. And for all that work, we got 10 points. And
Sorry,
that's actually,
isn't it positions 8 and 4 that stay ones?
yeah, 8 and 4 is 12.
Not 10?
8 and 4 is 12.
not 10, which is what
Yes.
we've been saying.
No, the question is, what value is in register 10? Initially, the value in register 10 was 10. But this command, this AND command, this second line here, overwrote the value that was in register 10. To what value did it now write it to? The value that we calculated by doing the AND of 28 and what was that? That was 14, I don't know, 15? 15, yeah.
Oh, it's not, and is not plus, right?
No, AND is not plus, AND is not add. They sound very similar to me, and it gets confusing. And add are two different things. And you should know what this is. Actually, they're talking. I saw one of the professors complaining that we should start teaching in Introduction to C++ how to do logical bitwise operations. But now you didn't learn it. But actually, now you're learning it. If I do an AND with these two things, it's called bitwise AND, which means that I compare bits. I do a logical AND on the whole string of bits and this whole string of bits, which means that I do everywhere I see a 0, 0, it remains a 0. Everywhere I see 0, 1, well, if it would be an OR, it would be 1 here. But it's not an OR, it's an AND. So 0, 1 is 0. Only the 1 and 1s will be 1s. So I'd basically go through every single bit and evaluate what it should be. And what I did was I realized that it's 0, 1 is going to be 0. 0, 1 is going to be 0. But these 1, 1s, this 1, 1 will be a 1, and this 1, 1 will be a 1. And from then on, it's all zeros, so it'll all be zeros. So my value will be all zeros followed by 2 1s followed by 2 zeros, which is the value 12. So that means the value in register 10 will be 12. Yeah?
I'm good.
Hello? Is that good?
Yes.
Great. So this is actually a time-consuming question, but not hard really, because you don't have to think. You just have to follow the procedures. You just have to dissect this according to the tables and follow the procedures. Just know that as long as you know your procedures, you can do this. And the procedures are just to figure out what the opcode is, and then divide up the number according to its fields based on that opcode and figure out what it is, and then understand the program. So B is actually going to be easier because, unless it has a key dude, let's see what B is. Given this, given this piece of code, keta code, given this piece of code, whenever it says a keta code, a piece of a code, or a section of a code section, it means there might have been lines before it and there might have been lines after it. Otherwise, it would say this program. See, this one says this is a program. This one says this is a section of a program. I mean, that's what it should mean. Okay. Now, what does he say? Oh, I'm still in this. Yes. So he's given the following section of code in assembly language. So we do an add with VI, with V0, and 0. Well, we know something about 0. 0 is always 0, so -1 goes into 0 and goes into VF. V0 is going to be -1. Then we say add together A0 and A0 and put it into A0. So if A0 was like 2, now it's going to be 4. And the next time if I do a loop, it'll be 8. By the way, this is add U, which means unsigned, which means that if I write it means that if I write a negative number, it'll view it as a positive number, essentially. It's assuming all numbers are positive, which means it's assuming A0 is not written in 2's complement, but is written in straight binary and there are no negative numbers. Therefore, the value in it, right. Fine. Anyway, not so important. He just wrote it that way. Well, maybe it's important, but I don't think it is. Add I. Now he says like this. take our V0, which was -1, and add to it 1. So now it's going to be 0. Now check. Is A0 equal to 0? Well, I have no idea what A0 is at this point. If it is equal to 0, then if it's not equal to 0, then continue the loop. If it's 0, then don't continue the loop, it'll end. Now, here he says, assume that at the beginning of the tokneet, register A0 has the value, some very large value, right? Some very large value. But notice that what this is doing is doubling the number. True? If it was 10, it'd be 10 and 10. If it was 20, it'd be 20 and 20. So this is doubling the value. So if this is my initial value, what did we, this is actually, he's being nice to you because he's giving you this 8 here. What's the next value it's going to be? If A0 starts at that, and the first thing I do is I double it, the next thing A0 is going to be what? 8 and 8. What's 8 and 8?
16.
16. So what will the value be in hex?
1 with a bunch of zeros.
Exactly. Very good. It'll be 1 with a bunch of zeros. And then the next time, what will it be? Let's count. That was 1 loop. What will it be next time? 1 doubled is 2. 2 doubled is 4. I got 3 times. 4 doubled is 8. 5 doubled, 8 doubled is 16. That's the 5th time. It's going to be 16, but I can't write 16 here because it'll go overboard. That 1 will be out of range, and essentially I shall have all zeros here. So A0 will equal 0 eventually, even though I keep adding to it. And that's why he did unsigned add, because I'm going to treat all the numbers as real positive numbers. Otherwise, it would like turn into a negative number and things would be weird. Okay, so it will go, in my opinion, the loop will go 5 times. So let's see. What will be the value of V0 when the loop ends? So V0 is a counter. The first time it's 1. So it's going to be 1, 2. It's going to be, let's count like this. It'll start off at 1, and then at that point, A0 is already doubled, so it's 1. It's essentially 1. It's 1 followed by a lot of zeros. That's A0, and that's going to continue there. Then it's going to go to 2, and it'll be 2. Then it'll go to 3, and it'll be 4. Then it'll go to 4, and it'll be 8. And it'll fail at 16, 5. So V0 will be 5. Does everyone see that? Was there a question? Something not clear?
I just have a question on the overflow. In MIPS, when there's overflow, like it doesn't stop the program or anything. It just keeps running, right? Like this would be like our responsibility to look out for, and we shouldn't have that happen. Yeah.
Well, first of all, let me answer like this. In this question, he doesn't give you the option of saying there will be an overflow. I mean, maybe. In addition, there's not going to be an overflow. In other words, I'll say it like this: there is such a thing as throwing an exception. The machine will throw an exception where there's overflow, but not in an addition of overflow. In a multiplication overflow, it'll throw an exception. And this is an addition one. But I mean, this is not a trick question where he's where the true answer is, well, I mean, even if there were an exception thrown here, V0 would still have its value. Oh, but it wouldn't. It would be 4, you're saying. You're saying maybe the exception gets thrown on this line immediately, and then it never gets to this line, and V0 will still be 4. So no, we're not talking about exceptions here. There's no exceptions being thrown in an add. It'll just loop around.
Like maybe I'm just like stuck thinking about C++, but like in my head, when there's an exception, your program kind of just like stops and that's it.
It does, but this is not an exception. This overflow will not throw an exception. That's what I'm saying. You're right. In multiplication, if I do a multiplication, oh no, it didn't actually. Say I take it back. Yeah. No, we throw except, sorry. So it's like this. The hardware may or may not throw an exception, but whether it throws an exception or not, the program will keep running. It's kind of like if you don't hit, like there's an exception there, unless you try to see if there was an exception, you can stop the program if you find out that there was, if you try to find out if there was an exception. But if you don't, then the program will just keep running. Yes. Even if an exception is thrown.
If we were doing multiplication instead of addition, it would be different.
No, I take it back. In multiplication, there would be an exception thrown, but it still wouldn't stop the program from running. Unless you manually did that, which we did not learn how to do. And you're not expected to know how to do. In C++, you have something called try and catch, right?
Yeah.
What happens if you don't try and catch, but then an exception gets thrown? So then it ends, right? So here's the opposite. All right, let's do a little bit more. So this is a good question. I mean, make sure you understand, what this is doing and what happens when there's, why that this actually will get back to 0 again. In other words, you can learn actually from this question something about programming. Here, it says, given the Keta code in previous section B, for each command, each instruction, write the encoding in hexadecimal. So I don't want to do that with you, but he's asking you to write 4 lines of hexadecimal encoding for these commands. And that's basically to do exactly what we just did in reverse order. Take this, we took this and turned it into codes. Now you're going to take this and put it into encoding. And now this, I would suggest you practice doing some branches and jumps in coding because they can be confusing. You can always compare it on the compiler. You can take some code and put it in the compiler and see what the compiler does to it. And then see if you can get there yourself. Try one out yourself at home. Take some command, try to write it into encoding, and then see when you put it in the simulator and you hit compile, or you hit assemble, does it come out the way you think it would? That's a self-test. Now, 40-point question. Given an array of data of size n, and each data is a word length. So we got an array of, let's say, n elements, and each element is 4 bytes. It's a word. And the beginning of the array is at location 10 million, 10,000. Well, that's the normal place. That's not a trick. That's just the normal place where every array would normally be in the simulator. 20%. Write a program that will replace the I element in the array with the n minus I minus 1 element. In other words, n minus 1 means just the last element, but this is minus I. So that means it'll basically take the last one and the first one and switch them. Then take this second to last and the second one and switch them. It'll basically flip the whole array around. That's what this means. Take element I and switch it with n minus I. There's the total size minus I. If I was 1, then it'll be minus 1. If I is 2, it'll be minus 2. So we're going in from the end and we're going forward from the beginning. And we're switching them. Now, there's a slight complication here because if I write this program, he obviously means that it should stop at halfway. Because if I don't stop at halfway, then I switch them all, I get to the middle, and now I unswitch them, and I got back to nothing. I don't think he means that. That would do nothing. And he says here, such that I is greater than 0 and less than n. Well, obviously. Okay. So he means that it's going to switch them, but, half with half, not switch them back again. So there you have to write a program. You're not going to have a question like this on the exam because it's a multiple choice exam. So I'll skip that. Let's look at this one. This is a little bit different. I mean, I assume you can do a program. Anyway, you should be able to do a program.
If all the questions are multiple choice in the exam, then the exam will look completely different, won't it?
No, it'll be, here's a line of code. I wrote a question for the Moed Bet where I wrote, here's some code. What is the encoding of this line? And then I give you 4 options, and you got to choose the right one.
Can you remind us?
The first question, will there be a question like that?
What question?
The first one.
Yeah, I don't know. I didn't write the whole exam. I only wrote one question in the exam, but for sure there could be a question like this. What's the value in register 10? So I could write 2, 4, 6, 8, 10. Choose, You got to write the right value. That's an easy multiple choice question. You still have to do all the work. You have to figure out what the value is. Or you could just guess. Okay, let's look at this question. Are there more questions?
Wait, how many questions did you say the test was?
I think it's 10 questions. Oh, which I don't like. I don't like multiple choice tests that are only 10 questions because you miss one and you're already down to 90. I like it to be 20 questions or 25 is best. But then it would be a lot of work because then you'd have take too long. So I think it's 10.
Do all 10 questions?
Sure, yes. Again, if you get a 50 on the final, you still can get 85 in the course. So it's not, and hopefully you won't get a 50. Hopefully if you get a 70 on the final, you miss 3 questions. So you'll only have missed 3 times, what is it? 5, whatever. You'll miss like 9, 3 times 3, 9 points. Okay. Where are we? This question 3. I'll end with this one. Actually, this is not such a good question to do because he just says, given this Boolean function, here's the function. Just understand the question. He's going to say, write a program that implements this function. Well, I don't want to write a program right now with you, but basically this is just saying, given 3 parameters, a, x, y, and z, the result of the function should be the value produced by this Boolean expression. Now, I think if you remember in Boolean, correct me if I'm wrong, what does this mean when you write X? First of all, it's X, not Y, right? Or what is that? Is that, no, so that's not X, not Y. That's not X, Y. What does that mean, not X, Y, in Boolean expressions? What does it mean X, Y? What does it mean X, Z in Boolean expressions?
And
Thank you. It means and. So this means and. And what does the plus mean?
or.
Exactly. So basically, I'm going to do just what I did before. I'm going to do a bitwise comparison between X and Y. And then I'm going to do a bitwise comparison between not X and Y. A bitwise and. When I say comparison, I should have said what comparison? A bitwise and between X and Z, sorry. And here, a bitwise comparison between not X, the opposite, is flip all the bits of X and take Y and do an and on that. Do an and on those two, bit by bit. And do the same, and do not Y and not Z, do an and on that. And from all those things, then take the first one and do an or with it on this one. And then do an or with it on this one, and you'll get some value. And that's the value the function should produce. So you have to use the, in MIPS, you have to use the and the or commands. See, we have exclusive or, but we have and also somewhere, probably at the beginning since it's A. And we'll have to use that command. This, you read this, you take this, and you get the and. So to produce this function, I don't actually need to do much. I just need to call the and function. I don't have to figure out the result is. I just need to write a function that will figure out the result. And then we have an or. Here's an or. Again, it takes the RS and the RT, does a logical or between all the bits, and the result goes into RD. Maybe we have time for one more. Let's look. Yeah. Given this program that we want to run on the simulator. Now, first of all, I want you to be not confused by this first line. Dot data 0x 10,010,000. That is the same thing as writing just dot data. What you're saying after that is you're saying, I want the data to start at location whatever, at location 10,010,000. Now that's where it starts by default anyway, so that doesn't actually affect the program. But it's his way of telling you that I'm assuming that the data is starting at this address. But theoretically, in the simulator, you can try this in your free time. You can write that, instead of writing dot data and then your array and your array, you can write dot data and then 0x, and then like you could write 10,010,004. And then you'll see that that it's moved over one byte, well, one word. It's not in its normal location. You can specify, is what I'm saying. You can specify where the array should start. Okay. So we started the array in its normal place, and we called the array mem, and we gave it some values, and each one is a word, and we made mem2. Looks like mem2 is empty, so it looks like we might be copying into it, but we don't know. Now he says text. Again, he says started at 0x 400,000. Hexadecimal 400,000. Well, that's where code normally starts. So he's not really doing anything by saying that. And then he says LA is load the address of mem into T0 and of mem2 into T1. Well, what's the question? Before I go on, I should know what the question is. That would be helpful. So what does it say here? Assume that the data segment, before running the program, is entirely 0. Okay, that's what we would assume anyway. How will the data segment after the running of this program how will it look? Copy into the table in your test booklet all the values that are appropriate. In other words, your job is to fill out all the data on this box. I suppose a lot of it would be zeros, but let's see. So the first thing that's going to happen is, where's the 10 going to go?
In the first box.
In the first box. And the 9
The one
in the
next
next
to it.
box. Remember, these are +4. These are, I mean, because these are words, they're going to fit nicely into each box. If this would be bytes, then it would be totally different. The 10, the 9, the 2, and the 1 would all be in this box. And it'd be hard to, and it would be in, in hex, it would be confusing. Actually, these small values would be not so confusing. Larger values would be confusing. But anyway, so the 10, 9, 2, 1, 3, 8, 7, 4, 5, 6, 0. And this block, the C, the 20C, will be empty. Will be zeros, all zeros. That's at the beginning. Then what happens? I do a loop and I copy I copy the 10 into T2. Then I check if it's 0. If it's 0, then I finish the program. So if I get to here, I'm going to end the program. But if it's not 0, I'm going to check. Is that value that I got less than 2? If it is, then make this 1. Then take T3, which is of course 0, because I didn't set it to anything, and put into it the value of this 1 that I got over here, which could either be a 1. Well, the first time it won't be a 1, it'll be a 0, because 10 is not less than 2. By the way, there's a mistake in this program. I can't believe you made a mistake. It must be somebody else wrote it. It should be S. Oh, I'm sorry, I misread it. It's not a mistake. I made a mistake. It's not SLT. It's SLL. Shift it right to. I made a mistake. It's not 10 anymore. It's going to be 10 divided by 2 is 5. Divided by 2 is 2. Right, in bits. You're going to shift it. Wait, shift it. Sorry, I'm again a little bit tired. It's left. Shift left logical. So it's not division, it's multiplication. It's 10 times 2 is 20. It's 40. You understand why? I shifted 10 left 1 bit. That puts it up to 20. Every time I shift something left, it goes double. And then it'll be 40 because I shifted twice. So T2 will be 40 plus T1, which is the address of this. Okay, you're doing crazy things here. So you're saying the address of mem2 is T1, which is what? Well, we said it's 20C. It's 10,000,000, 10,000, and 20C. And we're going to add to that 40. So 40 in hex is the same as 32 and 8, which is 32 is 2, so it's 28. It's 28. So we're going to add 28 to 40. And we get 68. Oh, wait, 40, no, this was decimal. Sorry, I getting confused. A little bit tired. 40, this is T1 is 40C. We're gonna add 40C to 28. So we're gonna get 8 and C, I'm trying to do this in my head. 8 and C is 20, so 20 is the same as 14. So it's going to be 10,010,054. That's going to be the value of T3, 54 in hex. Obviously, you do this on paper. And then I'm going to shift it back. That means the 10 that I got will have gone up to 40, and then I've added it to this, to the address of my T1. And then I put it back to 10. Then I go and I store it, and I store in that location. No, I store the 10 in the location that I created, 54, which will be over here, 14, 40 plus 14. You want me to do this on paper? You're not going to get a complicated question like this, but you're going to get, but you could theoretically get a question. I mean, you know, every time we try to come up with new questions that we never asked before. So there's a limit to how much this will help, but it gives you an idea of what you're trying to do. We're trying to see, okay, you know, is a great question actually, because it makes sure that you understand what memory is. When I stored it back, I stored it back to this T3, which I created. This T3 was basically adding 40 to T2. So that meant instead of it being, sorry, to T1, which meant that instead of it going where it should have gone really, which is like at the beginning of this array, it'll go 40 places forward. And then I increment T0 by 4 so that I get the next element. And then I'm going to multiply 9 by 2. Now, so essentially what I'm doing is I'm putting values in kind of random place, not random, but in computed places in this memory. This will remain what it was. The rest will be all zeros, but basically at this location, all of a sudden will be another number. And at some other 9, you know, where to figure out all the memory locations where I'm going to copy something until I get to this 0. Again, how did I calculate it? I took the number that he gave me, 10. I doubled it twice. I multiplied it by, well, I doubled it. I made it times 4. 10 times 4 is 40, right? This 2 shifting is like multiplied by 4. So it's became 40. Then I added it to my address. Then I put it back, and I put a 10 over there. So essentially, there'll be a 10 over in this place, 54. Wait, 54 is here, right? You understand how it's 54? This is 40 plus 14 is 54. So in this box, I'll have a 10. The next time, I'll have a 9. Where will the 9 be? The 9 will be in place, in the original place. plus 9 times 4, 36. But why did I say 1040? You think it's 1040? Am I right? T1. I mean, I made a mistake. T1. Where's T1 starting off at? T1 is starting off at the
1020
end.
plus C.
What?
At 1020 plus C. 20 plus C. If it
Yeah,
ends
that-
with the other one lead, does it
Yeah,
start
we
with the other one
calculated
in?
before. The 10 goes here, then 10, 9, 2, 1, 3, 8, 7, 4, 5, 6, 0. Here, C. 1020 plus C. Is that what you said? 1020C. So it should be 1020C plus 40. And 40 in hex, we said again, is 28. So it'll be 10. C and 8 is 1030, 1054. Yeah, I was right. I got 54 again. Yeah, it'll be here. Because I got to add to this. Yeah, I did it right. Sorry. I'm going to take this value, which is 1020C, and I'm going to add to it 40. But 40 is decimal, so I'm going to change 40 to 28. And then I'm going to say 28 plus 1020C, but plus 20C. Let's write that. Uh, 20C plus 40, which is 32 and 8, so that's 28, gives me 54. 54 is the location that I'm going to put the 10. And I'm going to go over here. 10. This is 40, 54. What about the 9? The 9 will be again 20C, but it'll be plus, instead of 28, it'll be plus 28 minus 4 will be 24. 9 times 4 is 36. That's 24. So it'll be not in place 54, but it'll be in place 50. So that will be right before it, one space. And the 2 will be 20C plus 2 times 4 is 8. So we can start to see a pattern here. Essentially, anyone tell me what the pattern is? Why are we multiplying it by 4 every time? And what's the pattern? First of all, we're multiplying by 4 every time because whenever you're giving an index of an array, if you give a 1, it really means 4 places forward because the array is jumping in 4 bytes. So I have to multiply every number by 4. So what are these numbers? These are the indexes where to put them. In other words, I'm saying put number 10 in index number 10 in this array in mem2. Put number 9 in index number 9 in this array. Put number 2 in index number 2 in this array. That's why I'm multiplying it by, that's how far forward I'm going. And then I'm putting 2 in location 2 in this array. So actually, if I would switch around the order of these numbers, it would have no effect. If I would, you see what I mean? I'm just saying, basically what this program does is it says, put 1 in location 1 in this array. Put 8 in location 8 in this array. That's why if you notice, these numbers never repeat. They're all unique indexes. So actually 10 will be the last one. So over here at 54, that's going to be 10. It's going to be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And the rest will be all zeros. And the first ones will remain what they were. So you see, I don't have to do them all. The minute I calculated 2, I noticed a pattern. And I figured out what was going on. And I could finish it. If I had to go through all 10 numbers, it would have taken me a lot longer. Better to think about if there's a pattern. Questions? Something not clear?
But before we end, I'd like to just ask you another thing about the final.
Yeah. I see everyone's very, very worried about the final.
Yeah, just
Yes.
because like I feel like I don't know so much exactly what to expect, especially like after seeing this. Like if we didn't do this practice exam together, I would never imagine that I would have to know how to encode for this final. Like for the other final and like with Avi, I would assume. But so I'm a little worried that there's like more things that we have to know how to do that we haven't like done in the labs. And I just want to know if there could be like maybe a list written up so we can just like check off that we understand each topic.
I hear what you're saying. Well, for example, this is not encoding at all.
Right, of course. But the first question we did was, and I happen to know how to do it because of Avi's class, but I wouldn't have studied it before your final, and maybe I would have been like forgetting some things.
Right. No, there's nothing else. I mean, you have to know how functions work. Everything else is in the lab. In the lecture of the lab, I have slides, and in those slides, I show you the encoding in the lab. In other words, this is material that is repeated in both, in both course and lab. If you go over here to this is what? This is the course. Let's go to the lab. There are not supposed to be any surprises. Here is the lab. Here. Wait a second. I left it. You're right. I didn't put it here. There. Let me go back. I do have it here, but it's only in Hebrew. Here are the slides are in English, but the title is in Hebrew, so I won't bother showing it to you. Matzeget shel Nachum Danzig al tichnut b'mips b'anglit in English, but that's the link that you're supposed to use for my course. But I'll show it to you with an English link to it. In the regular course, there is over here lecture 1 for both the course and the lab, by Nachum Danzig. This thing we actually went through before we went to Zoom. You may not remember, but we went through it and we pretty much did it all. We certainly did the beginning, and the beginning has in it this. Well, this, my friend, is encoding. I showed you, this is right in the beginning. So I don't know why you would think, we did this in class together before we started Zoom. We talked about the fields. We took a code, we took a program, and we encoded it. The reverse process, I maybe didn't show you, but once you know how to go one way, you know how to go the other way. Everything that is, nothing that it will be on the exam is not in this instruction sheet. So that is your preparation. Know how to work functions. And the assumption that you have done the labs and you know how to do the labs. So this, like I said, is for both the course and the lab. So when I teach the English speakers what Avi is teaching you, I use the exact same PowerPoint display, slideshow that I use in the lab that I used in the lab with you before we went to Zoom.
Okay, but basically what you're saying is that there's nothing that will show up on the test that you didn't talk about in this slideshow that you just opened.
That and the labs and the actual having done the labs.
Okay.
In other words, if you have successfully done all the labs and you have understood this single slideshow, then you know everything you need to know.
Okay, thank you.
These are the other chapters of what I teach when I teach the course. Okay, I will stop here, and I'll post this video for those who are interested.
Wait, I actually have one more question just about parameters with functions, if it's okay.
Yeah, one more question. Go ahead.
Yeah. You mentioned like in your video on lab 4 that if you change the parameters of a function in the function, you have to save it to the stack.
Yeah, I'm a little bit. I mean, that's a bit of a fuzzy question, but yeah, that's what I said. It seems to me like that. You could argue with me.
Why? Like why?
Why does it seem like? Why do I say that? I say that because when I pass parameters to a function, I mean, it depends how you think about it. But when I pass a parameter to a function, I don't expect the function to change my parameters. In other words, if I give it, it's a little bit confusing. In C++, you don't actually give it a reference, you give it a value. So it can't change. I mean, it's just getting a value. My thinking was that the caller, when he calls the function, expects that A0 and A1 will still have whatever value he put in them. Why would the function change his parameters? But you could argue with me on that point. I mean, I could be wrong.
You meant that we should save the values in the stack at the beginning and then like put them back at the end so that they would be the same when
That's
they
what I
come
meant. Yes,
out.
that's what I meant. But I suspect that there's a good argument to say that that you don't have to do that. You certainly could do that. Certainly wouldn't do any harm to do what I'm saying. It would certainly be the more prudent course of conduct. But you could argue no. When I call a function and I put something in A0, I don't expect that value to remain there. That was a value that I gave to the function, and I'm going to use it anytime I want to use A0 after that. I'll assume it has garbage in it. You could assume that.
Now,
The only problem I have with that assumption is then, if that's the case, then why is there V0 at all? Why are there return values? Just use the A's as your return values. If anyway the function is expected to destroy the values in the A's, then let him use those as the return values. And why do I need any V's? You see what I mean?
I hear what you're saying.
Therefore, I think the assumption is that the A's are not changed.
But sometimes when you write a function, like maybe I'm just thinking too much in C++ and it doesn't exactly line up, but from what I understood, everything in C++ gets translated into, assembly and then gets translated into machine code. And sometimes when you write a function, it's like a void function. You kind of just want to change the parameters instead of returning something.
No. A void function would not just change the parameter. I mean, and then print them out, you're saying? A void function, if it changes the parameters and doesn't return anything, then whoever called the function will not know that those parameters changed. How will he know?
Well, I mean, if you don't pass it by value, right? If you pass it as like a pointer and then like
yeah, it gets very complicated because if you're passing a pointer, if you think about it, changing the pointer is not the same as changing the thing that the pointer points to. The A, if you would think of A0 and A1 as two pointers, changing them would mean that I changed the value, the address that I was given, not the thing that the address is pointing to, not the location in memory. And that I would never do. Why would I do that? Why would I be given? You see what I'm saying?
Yeah, thanks.
We don't actually change parameters in C++. For example, let's say I write a function that says that takes an integer value and I pass it 7. I'm not going to change the 7. 7 is 7. In other words, I don't have to pass it a variable in a function. I can pass it actually a value. And the truth of the matter is, when I in C++ pass it letter A, and letter A has the value 7, the function has no idea about the existence of A at all. All he gets is the 7. He doesn't have any. It's almost identical as though I put a 7 there. In other words, if I call the function with the 7, or I call the function with a variable A whose value is 7, either way the function just gets a 7. And if he wants to change that 7 locally to an A, fine. But he didn't change the A that was put there ever. And the same with a function, with the pointer. He doesn't change the pointer. He gets a copy of the pointer. I pass a pointer which has the value 436 million, that's the location in memory that I want to change. He gets a copy, he just gets that value. He just gets 438 million. And he can change that to 439 million, but that would be dumb. I mean, then he's going to a different place. So I think I'm right that you really are supposed to assume that the A's did not change after the function call.
Thank you.
But you could argue against me. You could argue against me and say, no, I should assume that they're destroyed. They're just temporary values. I don't know. You'd have to talk to a bunch of experts in this field and see what they all say. All right, so we'll stop here.
Are we meeting again next week?
I don't think so. I think that's it. I was planning on doing 2. I think that's enough. I mean, I'm very responsive. If you have questions on the homework, I tend to answer them within 10 minutes or within a day or 2, but often within 10 minutes. If you're doing your I expect actually that you're writing me when you get stuck on a certain part of your homework. That makes me feel good because then I see that you're doing your homework. So you can write me emails, and that way I can help you with your homework. I think it's more effective than a Zoom class. But you have to take the initiative and write to me. You meaning you plural. So no, I don't think we'll have another class. Unless there's some need, you can write to me and we can do that. Okay, we'll stop here.